Okay, so you can't see moving vibrations, you can't hear the engines going, whatever. The shades are drawn, so you can't see trees whipping by you and so on. And so you just wake up in the morning, and whatever. You're the same as before. You play the game of billiards, you shoot a ball like this, you say, oh yes, that angle, and when I shoot one ball or the other, I observe the conservation of momentum and all that kind of stuff. And so you observe that the game of billiards plays out exactly the same as it did the previous day. Okay? So the point here is that the velocity of the train on day one was at rest with respect to the tracks. On day two, it's moving with respect to the tracks. The velocity of that train with respect to the tracks has no effect on the way that these balls behave. In other words, there's no way, by making observations about how the balls behave, that you could get any information about how fast they're going. Okay? That's a very important point. That's basically what this principle of relativity is saying. So, let me say it this way. So, no way to determine velocity I'll just say it again slightly differently. What it's saying is that the unaccelerated motion of a system, of a room, has no effect whatsoever on the way things behave, the way things happen in that room. And that's what it means. Okay, so let's talk about whether this principle is, or this idea, this principle, T1 here, is believable or not. Okay, well, first of all, it's obvious. It's certainly 1905 would have been completely obvious to anyone if you apply this principle to mechanical phenomena. Okay, and it had been obvious for mechanical phenomena like billiard balls, like soccer balls, like cars, like whatever. It was totally obvious for mechanical phenomena, even all the way back to Galileo. Even Galileo knew this. Newton certainly knew this very well. Everyone knows this. Okay, but it's not so obvious for electromagnetic phenomena. Okay, so he's not electromagnetic phenomena. Okay, so why is it not obvious for electromagnetic phenomena? Well, at the time, in 1905, so as I said, a lot of physicists had this picture of light as a wave moving in ether, like a sound moving in air. So, for example, suppose we go with that. Suppose we imagine that light is a wave in ether. And we consider the following simple experiment. Okay, and the same thing would apply for sound in air. Same kind of an experiment. So the blackboard here represents either the ether or the air, depending on whether we're dealing with light or sound. Okay, so that's sort of this backdrop. So we're going to have things floating around in this ether or this still air. Okay? And the first thing we're going to have floating around is a reference frame like this, which is at rest. So a room which is at rest with respect to that ether or air. And we have a source of light, which is a light here. Okay, we have a flashlight over here. And what we're going to do is click on this flashlight and we're going to do a simple experiment. Okay, so we've got Alice inside there, and what does she have? She has a ruler and she has a clock. And she's going to measure the speed of light. Okay, so she clicks on this flashlight, and light is a wave in ether. What that does is it sets up a disturbance of the ether here. And that ether vibrates, and the disturbance moves like dominoes. What does speed C relative to the ether? Alice is at rest with respect to the ether. What speed does she measure? C. Okay, so she says, oh yes, C. Okay, now we consider another situation. Okay, so unbeknownst to Alice, in the middle of the night, her little room is accelerated and is now moving at some velocity, drifting with some velocity v relative to the ether. Okay, so she gets up in the morning and she conducts the same experiment, very complicated experiment. She conducts the same experiment again. Okay, she's got her ruler here and she's got her clock and so on. She does exactly the same experiment. What speed is she going to measure now? Okay, so let me say C. We're assuming wave in ether. Light is a wave in ether. Okay, so just like sound in air. Okay, so don't imagine, don't assume anything about relativity, anything you know about special relativity. Just go back to the 1800s, think about light as a wave in ether, and you are moving with respect to that ether. You are drifting this way, and the sound is coming, the light is coming at you this way. What speed are you going to measure? So let me say C. Let me say C plus C. Okay, so if you're going to measure C plus C. Okay, and let me sort of re-emphasize this. What's going on here? If we imagine that light is a wave in ether, then what is this flashlight doing? What it's doing is it's grabbing a hold of that ether, that mechanical medium, and it's jiggling it around. Every time you set up some kind of disturbance in that ether, that disturbance moves relative to the still ether. It radiates outwards in all directions relative to the still ether. So as this flashlight, even though this flashlight is in motion over here with respect to the ether, okay, the waves move at a speed c relative to the still ether. Okay, so here you have waves coming at you, or moving with respect to still ether with speed c, but you're drifting in that ether towards those waves. Okay, so you're going to measure c plus c. Okay, so on day one, Alice finds she does a simple experiment involving the electromagnetic phenomenon, namely light. Okay, and she finds that, oh yes, the speed of this strange stuff called light is c. Okay, and then she wakes up the next morning, repeats the experiment, and finds a different result. Finds now C plus D. And says, whoa, something has changed. And so she can then determine something about the motion of her room based upon observations of a physical phenomenon confined to the inside of that room. Okay? So even though the room is sealed, okay, all the windows are drawn, all the blinds are drawn, she can't see outside, she can't see if she's moving from the day before or not or whatever, she can just conduct a simple experiment that takes place entirely within her little box and determine something about the motion of her box. Okay? So that's completely counter to this relativity principle. Okay? So it was not at all obvious at that time for electromagnetic phenomena. Okay, and that was the problem. Okay, so what Einstein wanted to do is say, this is such a simple and beautiful principle that we would like to extend that from mechanical phenomena also to electromagnetic phenomena. So Einstein wanted both. In fact, all physical phenomena. He wanted it to be true that anyone in any inertial motion, non-accelerated motion, can consider themselves to be at rest, exactly as if they're at rest with respect to this ether. Okay, so the results of any experiment don't depend upon your motion. Okay, so everything that happens inside, any physical phenomenon inside a closed box, happens the same way, regardless of the motion of that box. You can't determine the motion of doing experiments inside the box, whether those experiments be mechanical or electromagnetic. The results of all experiments are the same as if you were at rest, in quotation marks. Okay, so the point here is, if light is a wave in ether, there's a problem with this principle. It's not obvious that it applies. But what if light is not a wave in ether? Yeah. So that's one. I think that one is a big visible one. Yeah. So when you're I'm talking about area stuff. It's a problem with the area that's moving towards the thing called the inside the box. Yeah, so that's a good question. So if we think about this as air, and we're moving with respect to air, then what we are imagining is that the air can pass through. Okay, so that when this person is moving with respect to the air, the box is not completely sealed. Okay, otherwise the air would be at rest with respect to this person. Right? So we imagine that person is actually standing on a platform, an open platform like this, and drifting with a velocity d relative to still air. Okay, and then we would see C plus D. How do we know that actually still moves air in the box? Yeah, that's a good question. How would we know that the ether wouldn't just drift along? So here's a massive object like this, and maybe that the massive object would grab onto that ether and drag it with it. Okay, so people thought a lot about that sort of thing. And they concluded, well, that can't be happening because, suppose that the ether were some physical substance. Okay, and if that were happening, then here's the sun, and here are planets going around the sun like this, then those planets would also be dragging ether along with them. And if the ether is any kind of a physical substance, that's going to produce a drag. And then the planets would actually slow down and spiral in. And so they made careful measurements of the planets. They didn't see any of this spiraling in. Okay, and lots and lots of experiments were done to try to detect, drag and fluids moving and so on and so forth. And it was a very complicated set of ideas floating around here. Yeah, that's right. That's right too. So if it were true that material like matter moving through that ether dragged the ether, then my parents would drag the ether as well. And I could just go like this, and I would be sitting on vibrations of that ether, and I would be radiating light. I'm over right? So okay. So there are problems with this whole ether, with this whole mechanical law of light. Okay, so the question then is, okay, so it's clear that if you have a wave in ether in mind, it's clear that there's a problem with this one here. Okay, it's not consistent. But what if light is not a wave in ether? Okay, what if light is not a mechanical vibration of some physical medium? What if light is itself some kind of physical medium in its own right? Okay, so at the same time, in the same year, Einstein wrote a number of very important and influential papers. And one paper that came just before the special relativity paper was his paper, it's called the photoelectric effect paper. How many of you are aware of this paper? Okay, so what was the goal of this paper? The goal, or at the beginning of the paper, Einstein states very clearly the goal. The goal is to try to understand, or to try to bring electromagnetic phenomena on the same footing with mechanical phenomena. Okay, so for example, you think about say a baseball. I throw a baseball like this. That baseball is moving through space. If I go into empty space, I can throw a baseball and it can move through a vacuum. Okay, so I can have a chunk of matter moving through a vacuum. And that chunk of matter has various properties. It has energy, it has momentum, it's spinning, it has angular momentum, all that stuff. So I can have matter moving through a vacuum and having energy, momentum, angular momentum, all that stuff. What if light is not a vibration of some existing material filling everything? What if light itself that light has momentum, light has energy, light has angular momentum. It has all those properties that ordinary, like a baseball has. Okay, so Einstein said, well, suppose that light is not this sort of thing, that this vibration of some physical medium filling all space, but it is a medium of its own self. It is matter. It is like matter. If he was trying to put electromagnetic phenomena on the same footing as matter at that time. Okay, so then, if that's the case, it is reasonable to try to extend this principle to apply not only to mechanical phenomena but also to light. Okay, so that's the basic point here. So let's say it's down here. So it is reasonable. To extend principle K1 from applying to just mechanical phenomena also to light, because Einstein was trying to put mechanical phenomena and light on the same footing. Okay, so the immediate problem with that is that if you take the relativity principle and you take Einstein's statement of the constancy of the speed of light is independent of motion of the source, both of these are very believable. Okay, so even if you've gone of wave and ether or whatever, this would be obvious to you. That's the equations of this would be obvious to you, etc. And this is also very believable. It's something very natural. If you could put, think of electromagnetic phenomena as physical phenomena in its own right, carrying momentum, angular momentum, and all that, just like a mechanical, baseball floating through space, then it's reasonable to try to expand the relativity principle to include light as well. So these are two believable principles. There are two starting points that everyone in 1905 would have said, yeah, that's reasonable. If you take these two together, they imply this P2 prime. And so I will leave this as an exercise here to show that logically these two apply this one. Okay, now this one here is totally unbelievable. Remember, this is the one that's saying that if I have a flashlight at rest there, I will measure a speed c, the speed of light, whether I'm running toward the flashlight or away from the flashlight. That makes no sense whatsoever. Okay? But these two are very believable together, so by them in and of themselves, they're not radical at all. But when you combine them together, they predict something totally radical. Okay? So the point of special relativity is to try to understand how this is believable, how this is natural. Okay? And it required a complete revision of our understanding what space and time are. Okay, so having said all that, let's get back to this diagram over here, and let's think about how we determine that K. All right, so okay, so remember that when we're dealing with simple sound in air, we determine K just by assuming universal time. So that Cc plus D is equal to Kcc, and that gave us the Doppler shift. Okay, so what we're going to do is we're going to replace the idea of universal time. We're going to replace that assumption with the relativity principle P1. Okay, so I would much sooner accept something like the relativity principle, which has a real feeling of something universal, a universal truth about our universe, and something very natural, and something that simplifies things. Okay, so I would much rather accept this than accept this sort of ad hoc universal time assumption. Okay, so we're going to drop the universal time assumption and replace it with V1. Okay, and then we're going to determine what K is, and we'll find that K is not the same value that we had before, and we find that Bob's time is not the same as Alice's time. Okay, so how do we do this? So this is actually a very important point that we've reached here. Okay, so if you've been sleeping up till now, now's the time to wake up. Okay, so this is the most important part right here. This is the part of special relativity. This is all of the logic of special relativity in the next two pictures. Okay, so let's take this picture over here and let's draw sort of a simplified version of it. Just look at a corner of that picture. Okay, so what we've got is Alice at rest. We're taking the point of view that Alice is at rest, so her world line is vertical. So this is Alice at rest. Okay, and what she does is a simple experiment. What she does is, at some time on her clock, when her clock reads 0, what she does is she takes the second clock and she zeroes that clock. She zeroes both clocks at the same time, and she zeroes that clock, so that clock drifts with respect to her with some velocity v. Okay, so previously we had called that Bob. Okay, well, she picks up Bob and throws Bob across the room, and Bob's got a clock attached. She's not interested in Bob; she's interested in the clock attached to the wrist. Okay, and so Bob is drifting across the room like this. She waits a time t on her watch, and then she sends a light signal chasing after Bob. Okay, and that light signal, when it reaches the clock that Bob has, the clock is designed to freeze, stop time. Okay? And then what Alice does is, afterwards, she runs after Bob, she grabs hold of him, looks at his watch, looks at what the frozen time was. She looks at how much time he lasted on that clock that she threw across the room. Okay? And according to our picture here, it's going to be whatever time is here, the time here is k times that. Okay, I'm just dropping the C. You can also put C here. I'm just dropping the C. Just to simplify the picture. Okay, just to focus on the main point. Okay, so whatever time Alice waits, this time is KT. We don't know what K is. We're trying to figure that out. Okay, so Alice does a simple experiment. She throws a clock with a velocity t, waits a time t, how much time elapses when the clock receives that light signal. Okay, so she does a simple experiment. Okay. Now we're going to apply the relativity principle. So the relativity principle says that for any two observers, any two inertial observers, given to any two inertial observers in uniform relative motion. Well, this is certainly true. Imagine Alice and Bob are just floating out in the middle of empty space. Okay, from the point of view, take the point of view that Alice is at rest, she sees Bob here to the right, which comes GT. But we can also take the point of view of Bob, who just looks at Alice and says, no, I'm at rest, and you're the one who's moving with the speed minus d in the other direction. So given any two inertial observers in uniform relative motion, this certainly applies to Alice and Bob. They're in the middle of empty space drifting around with a relative velocity d. Both are equally entitled to consider themselves to be at rest. Okay, so Alice has done this experiment from the point of view that she is at rest. Okay, now we will allow Bob to do exactly the same experiment with him at rest. So how do I draw Bob's world line? Okay, so Bob's world line is like this. So it's now Bob that we're taking to get rest. And Alice is moving backwards. Alice is moving this way. Okay, and Bob's going to conduct exactly the same experiment. What he's going to do is, so he's at rest, and Alice is drifting this way, or rather just her clock is drifting this way. So he picks up Alice, he throws her this way, with the speed d in the other direction. Okay, and he waits a time t on his clock, and then he sends a light signal chasing after Alice's clock. When Alice's clock receives that light signal, the time freezes, and then Bob comes running after Alice, catches up with her, looks at the time, and then he elapses on her clock. Okay, so there's a time t. What is the time here? Okay, it's also kt. Okay, it's the same k here. That's important. Okay, so according to the principle of relativity, we've got a situation of two inertial observers in uniform relative motion. They are equally entitled to consider themselves to be at rest. Equally entitled to consider themselves to be at rest. Okay, so the result of and they're doing identical experiments. Okay, so the results need to be identical. Okay, they can't actually be able to distinguish who's actually at rest, and Bob who's actually at rest, or Alice is actually at rest. Both points of view are equally valid. Okay, and so if they're doing the same experiment, they should get exactly the same result. So this is the same experiment. Okay, so that's it. So is that clear? Are you happy with that? And if you understand that, then everything follows. Everything follows from this. Okay, so let's see what follows from this. So far, does it seem reasonable and natural? Does it seem believable? Okay. Right. So now what we're going to do is we're going to take that picture and we're going to make two modifications to it. The modifications contain no physics whatsoever. Okay, they're just looking at it from a different point of view. Okay, so the first modification we're going to do is so Bob has done an experiment in which Alice is in motion and so on and so forth. We're going to take Bob's experiment and we're going to look at it from Alice's point of view. Okay, so now Alice's world line will be what? Okay, Alice's world line is vertical like this. Okay, and if Bob is drifting to the right. Okay, but Bob is the one who's doing the experiment. Bob is the one who waits a time t on his clock and then sends a light signal over to Alice. And how much time has he elapsed on Alice's clock when she receives that light signal? KT. Okay, so we have this picture. So I haven't done anything here. All I've done is I've taken that picture, the information in that picture which says Bob waits a time t, Alice. Picture. Okay, so in this picture we have a T here and a KT here. In this picture we have a K. See, you'll notice that this triangle here is the same as this triangle here. Okay, so this side is KCT. So we want actually a KCT here instead of just a T. But the fact is that no matter what, the T here is arbitrary. T could be 5 seconds, 5 years, whatever. The point is, whatever appears here, to get what appears here, you just multiply by K. Okay, so we can make T anything we like. Okay, so let's make T. Put on the exact same picture, and we will replace T with this thing, K times CT. Or just KT, let's make a KT, sure. Okay, so if this is KT here, what is this? K squared T. Okay, now in this picture here, I've been plotting TA and TD. It's just time here. But we know that we want to actually put C times TA, C times TD, which means we have C's here. Okay, so now this picture here now looks identical to a certain subset of this picture, which is this triangle over here. We've got a KCT here. And so, okay, so the result of this then is, are we okay so far? All right. so if we're okay, let me ask you, if I look at this picture and I compare that picture with that picture, what can I learn about it? What can I learn about the situation?